Okay, so today's video is going to be about quantum mechanics. Okay, and in that we will be talking about we will be talking about states. When we talk about in quantum optics and quantum optics, we take the states as 1 and 0, but in other areas like quantum quantum computing, quantum computing or computers, we take it as 1 and wait, no, it was opposite. This is 1 and 0, but here it's 1 and well, it doesn't matter that much, so but this is how we should take. Okay, these two together can be written as psi. This single symbol defines both, and what I mean by the defines both is that if I expand the psi, what we get is that c this plus c, let's suppose c, I'm making it c this. Okay, the thing that these two should equal 1. Psi alone defines state 1 and state 2, but these two states together should equal 1. So if I want to write how it should be, it's the state probability of 1 C1 square plus the state probability of C2 equal square equal 1. This shows that the probability of a certain object being in or not object particle being in state 1 is certain value plus the state being in C2 has a certain value, what are the probability of it being in both, and the probability addition should result in 1. Okay, so then when we talk about states, what the states actually are in quantum mechanics, by states I mean superposition is what states are used for or because in superposition a single particle can be in multiple states. Let's suppose it can have a spin of up plus it can have a spin of down. So I can write it as spin. I can write it as spin up and spin down. But this is, always remember, we measured something, we think of a state or a particle in being multiple state is when not observed. This should be a highlight, a key point when not observed. This is a key point here. Not observed means the measurements are not taken. When the moment the measurements are taken, this particle will break its what do you call that, its phenomena, what phenomena it has, it will break, and that will cause what, it will cause the object or the particle to have either spin up or spin down. So either one when measurement is taken. Okay, so psi of x, sorry, not psi of x. Well, yeah, we can say it's psi of x and t. This is why what I mean by x and t. It means the evolution of that particle through space and time both equal c1 plus c2. This is, I'll highlight it, when not measured, but the moment observed, what will happen? Either we get C1 or we get C2. So then it will be fair, then it will depend on the probability calculation. So this is C1 and this is C2. Then we talk about, well, this symbol psi can have multiple variations. It can either be psi of x and t, it can either be psi of x, it can either be psi of t. Yeah. So this is the one in which both position and time are measured. These two are independent of each other. Means, or if you measure s psi of x, that means you're measuring the particle in space and you're not measuring its evolution through time. You're only looking at its position. So then these are two just different ones. Okay, then we have superposition psi of x, this. Okay, so there's a way to create the states in entangled state. States in entangled, meaning how can we make two different states? Let's suppose state 1 and state 2, or how can I say this? We can say that two particles or two photons, when you squeeze them when you squeeze them, what will happen? They will have a squeezed state, two squeezed state mode or something like that. What will happen is that these two particles that when you squeeze these two particles and in a two mode system, they will entangle with each other. They will be an entangled connection. And one more thing, the stronger the squeeze, directly proportional to strength of the, or strength is strong, or strength of the strong, no, let me just say strength of the correlation. We call it correlation. Correlation. So the correlation will increase. Meaning, okay, here then one more concept will come. Heisenberg uncertainty principle. Heisenberg uncertainty principle. Uncertainty principle. And in this principle, what we will be talking about is that as the correlation of the squeezeness of these two increases, the Heisenberg uncertainty principle will also develop. What I mean by Heisenberg uncertainty principle is that psi of p dot psi of x, not psi, delta, will h bar over 2. So, what is Heisenberg uncertainty principle? It is that if one thing increases or one measurement of one affects the measurement of the other quantity, so what will happen here is that increase in correlation, increase in squeeze, what will happen is that increase will cause x. Let's suppose we are measuring x, it will increase, but in respect to that, what will happen is that p will decrease. Okay, and what we have at h bar is reduced. Planck's constant. Okay. H bar is nothing made from h. It is h bar over 2 pi if I'm right, something like that. Okay. So if I want to write the correlation between these two, that how the correlation could be made up in terms of mathematics, I would write it as, because we're talking about momentum. What is momentum? Okay, and x. Position. Okay, if I want to write the states, these two squeeze states, how will I write it? I would write it in quantum states. I mean, psi of x1 and x2 equal square root of 2 over pi. E of exp means exponential of minus e of power 2r minus 2r of x and, or let me just write it on the other page down there, and this will give us minus e of my power of minus 2r of x1 plus x2 square divided by 2 minus e of 2r p1 plus p2 square. This is the separate one. This will be separated to minus. Yes, this will be separated by the other one, minus e of plus 2r of x1 plus x2 square over 2. This is the first one. The second one is momentum. Okay, here's the difference. For psi of x and x1 and x2, we don't have a bar on the top. For the momentum we have. So p1 plus, not plus, p2 equal to 2 over pi. Same thing like this, but the only thing or the only difference we have is instead of x1 and x2, and over here we would write p1 minus p2. I'll just write this because I don't have space. p1 p2, then minus p1 plus p2. So the difference is that at first we did x1 plus x2, then we did x2 x1 plus, this is minus, this is plus minus, so same here as well. Okay, then this is known as, we can write these two as C of this x1 minus x2 for the first one, and the second one is we have p1 plus p2. This is known as, if we simplify it, Wigner function. Wigner function. Okay, if I want to write in the Wigner function, what will I write? 4 over pi square of x potential of this minus e of power minus 2er of x1 plus x2 square plus, so first of this one and then this one, p1 minus p2 square. This is our first one, taking the x1 plus x2 of the first one and my p1 minus p2 of the second one. This is the first one we made with addition to, not addition, subtraction to x1 minus x2 of the first one square plus p1 and p2 of the second one, then that's it. We just made two of them. Okay, now notice one thing here, that we took the positive of the first one and the negative of the second one, and positive of negative of the first one and negative of the second one. This is the Wigner function. Wigner function. With this, what we have is that it approaches C of this x1 minus x2 of, this is I think a symbol, it's an imaginary symbol, p1 plus p2 in the limit of infinite squeezing. So it says, in terms mean we are trying to squeeze the, what do you call this, r, or what we have, the distance corresponding to the original perfectly correlated and maximally entangled but unphysically APR state, or is from, what, one more thing, this all is from APR paper. This all is in APR paper. Yeah. Okay, so then from the Wigner function, the marginal distributions of the, for the two position or the two momenta. Yeah. So what was here? What is x? X is position. X is position, and P is momenta or momentum. Momenta or momentum. We take it as momentum mostly. Okay. Then okay, this is a way, a mathematical way of approaching, or we can make more squeezed entangled states for a photon. It could be for a photon or anything similar particle. Similar particle. Okay. So let's study a little bit of this. What we wrote here. Square root of 2 over pi psi of x1 plus x2, x1 and x2. First of all, we made the equation for psi of x1, or wave function of x1 and x2. This E shows for exponential. X1 plus x2, first we added these two, divided by 2 minus the same thing, but here we had negative 2 power 2r, here we have positive power 2r, and x1 minus x2 for the second one, and then again divided by 2. Okay, then we made for momenta 2 over pi, same thing, minus e power minus 2r of p1 minus p2, then divide by 2 minus p plus 2r power 2r of p1 plus p2. So it's vice versa, here plus, here minus, plus minus, minus plus, and this is how we can describe it. CF, okay, for both x1 and p1, because when we combine these two together we make does this give us plus, or is it plus, or we added him? We plus or 4 over pi square. This is how this came into existence. Square root and square root cancel each other, and 2 times 2 is 4, and pi times pi is pi square. Square root cancel each other, cancel each other. And then psi of x1 and x2, this is, okay, let me write this. Mathematical or maths of quantum optics, making two states in full, two squeezed states. It's a mod. Thank you.